Joe, Max and Ron, I've been trying to call with the landline, and it keeps giving me a busy signal for that phone number, and I had that problem when I called in with my cell.
The number that's on here?
Yeah, the phone number that's there. I eventually got through, but I was getting a busy signal for about 3 or 4 times, and I'm getting it now with the landline I'm trying to call in. I don't know if other people might be having that problem.
Try another number then.
Hey Max, this is Rob Yemi.
Hey Rob, you have a
I came in fine.
Okay. I gave another number up there, so people need that, they can use that one.
This is Joe, and I used the 860 number, and I got in fine.
Yeah, I think they give you, from what my experience with Join.me, they give a multitude of dial-in numbers, but the access code is what is key. So if you have the right access code, the multitude of numbers doesn't really bother it. We'll get started in a minute or two.
And Max, I'm going to mute my phone.
Thanks.
Hey, Ron.
Hello.
This is Jordan Stacy, and I'm upstairs.
Okay.
Get started. Go. Good afternoon. I'm Ron Smith from the OBIC Bioproducts Innovation Center. I want to OBIC Bioproducts Network. Latest presentation is part of our Bioproducts Commercialization webinar series. Today's webinar will cover the USDA Biomass Research and Development Initiative project. We're fortunate to have key staff from OARDC and Peter with us as presenters today. We will also give everyone a brief overview of the World Tour project to promote bio-based products and bio-based science. Before we start, let me highlight 2 quick logistical issues. First, if you've not already done so, please be sure your audio connection is on mute to reduce audio interference and feedback for our recording. Second, if you'd like to ask a question of our speakers, we'll have a few minutes after the presentations. You can submit those questions directly either via the chat box on the right-hand side of your screen, or the best way is to email directly to max@maximumcq.com, and then we'll pass your questions on to our speakers for them to answer. With that, I'd like to begin our program by introducing our first speaker for the afternoon, Ms. Jordan Stacy. Jordan is one of our student interns here at OBIC, and Jordan is majoring in agricultural communications. Okay, take it away, Jordan.
Hi, I'm a student assistant for the Informal Education and Media Relations underneath Dustin Ullman, and so today I'm going to talk to you a little bit about the Sustainable World Tour and some of our education initiatives and ways that. Do you want to go to the next slide, Ron? Perfect. Okay, so the OBIC Education Department consists of 2 complementary branches, formal and informal education. The formal education is centered around BBEP, which stands for Bioenergy and Bioprojects Education Programming. OBIC uses this curriculum to educate both teachers and students on bio-based concepts and activities inside and outside of the classroom. The informal education half is where I am focused. It is important to OBIC to educate consumers on the importance of purchasing bio-based products and their role in sustainability. And it is through this effort that OBIC has launched the Sustainable World Tour. These 2 pathways are trying to create a greater consumer demand in order to expedite the commercialization of bioproducts. And then that leads us to the bio-based promise, which is what OBIC is based upon. Through the Sustainable World Tour, we're communicating this mission to consumers and the general public. You want to head over? Okay. To the next slide, Ron. It is because of so this is what some of our networking for the Sustainable World Tour consists of. So these companies make both our formal and informal education initiatives possible. And just to pull out a few, Ford donated the van that we use to transport the Sustainable World Tour, and the Ohio Soybean Council is partnered with us to make soy-based lesson plans and workshops and other funding possible in order to make this executed properly. Okay, and then this is actual the Sustainable World Tour van. So the Sustainable World Tour is transported by a bio-based vanded brand and has a variety of hands-on lessons that consist of STEM, regular lessons, workshops, and demonstrations. These activities are centered around bio-based and sustainability concepts, and we use this to educate both teachers and students. So the teacher component is we educate teachers at a week-long conference, or we'll go out and visit them, and then the student component is we will actually go to classrooms and set up teacher workshop for the teachers. So it's essentially to educate them on making smarter choices today that will produce a better tomorrow. And then, so this is some of where we've been since the tour has launched, and mostly we've traveled across Ohio and the Northeast United States. So we've attended Ohio FFA Convention, the United States Department of Agriculture in Washington, D.C. We've gone to a Dayton Dragons game, the 4-H STEM camp at Camp Cantor's Cave. We actually did a workshop here in the right bottom corner. You can see some of us goofing around afterwards teaching a tech camp to some extremely smart students here on Ohio State's campus. And then going on through the rest of 2014, we are attending the Ohio State Fair, the Farm Science Review, National FFA Convention, and we hope to continue with different school programs as well. And then that kind of brings us to the end, but if you want more information on the tour, you can visit sustainableworldtour.com, or you can email us questions about sponsorship, because we would love to promote your companies and have you involved that way, or you can email questions or anything like that to sustainablewt@gmail.com. Or if you just want to keep up with what we're doing, you can follow us on Twitter at sustainablewt. For any further questions or things that are kind of outside of you may be confused upon, or you just want to inquire some things, you can email me personally at stacy.114s@osu.edu, or like Ron said, you can send them to Max.
All right. Thank you very much, Stacy. Appreciate it. Speaker for the afternoon, Mike Sword. Mike is our project lead on covering today. Mike also provides engineering support to many of our projects with other OBIC clients as part of his outreach. Mike has a Bachelor of Food, Agriculture, and Biological Engineering from Ohio State University with specialization in power and machinery systems design. He also has a master's degree in agricultural and biological engineering from Penn State University. Mike has 15 years of professional industry and research experience in agriculture and safety focused on mechanical systems. Many of his projects have included harvesting, material handling, and chemical application equipment development. He's worked in industry as a design engineer and has led testing and research programs to develop new solutions for today's industry challenges. Mike is also the recent past chair for the American Society of Agricultural and Biological Engineers, the Ohio section. With that, go ahead and take it away, Mike.
Thanks, Ron. I want to thank everyone for their time today to let us talk about one of the programs we have going on here up at OARDC and at the Ohio State University. We call it the BRDI for short project, but BRDI stands for, what does BRDI stand for? It stands for Biomass, Research and Development Initiative. So it's the Biomass Research and Development Initiative. We call it BRDI so much we forget what it actually stands for. But it's a NIFA program, USDA NIFA grant. This presentation is going to give you kind of an overview of that program, and then Jose coming afterwards will talk about some of the work that we have been working on, Jose and myself, regarding this particular project, but there are many tentacles to the project, so we're kind of excited about this one. Okay, go ahead, Ron, you can move the slide. First, I'm just going to give a quick anaerobic digestion 101 lesson. Many of you probably know about anaerobic digestion, but I think it's appropriate to just give a quick overview. That's really the crux of what this project is wrapped around. talk about the project overview, the goals, and the current going on with the BRDI program. Next. And then kind of a so what. Why does it matter? Okay, move on. The formal definition of anaerobic digestion is anaerobic digester itself is an airtight, oxygen-free container that's fed with organic material such as animal manures or food scraps, and it's a biological process occurs in the mixture of produced methane and CO2. Well, we call it biogas, and it has an odor-reduced effluent. It's not odor-free, of course, but microbes break down the manure into a biogas and a nutrient-rich effluent. That's kind of just the crux of anaerobic digestion. We have a lot of these systems. You hear a lot about them coming up on farms, a lot of our wastewater treatment facilities. Quasar here up at OARDC is kind of leading the commercialization of some of this technology. Okay, move on. Basically, it's what happens in a cow's stomach is what that last piece was. So just kind of a graphical description of what happens with anaerobic digestion. You have an organic material. It could be food waste, a yard waste, a manure. It goes through a bacterial digestion. We get kind of two streams from that, two co-products, a biogas. It's roughly about 65% methane, 35% carbon dioxide, and then an effluent, which could be solids and or liquids. From those two co-products, we try to create some value-added products. It could be heat and electricity with a combined heat and power system. Also, we do some CNG with this biogas and power some of our CNG vehicles, which is becoming a popular thing. And if you've been following some of our agribusinesses around the state, they're converting whole truck fleets to CNG. It's kind of an exciting thing. And then the effluent side, it's being used in compost and also as a soil amendment. So those are kind of really the co-products coming out of these digesters. Bacteria breakdown of organic material happens in a series of stages. You have carbohydrates, fats, and proteins in this system, and you break them down into sugars or fatty acids and amino acids, and from that into carbonics, and then you get down to your methane and your CO2. This community changes throughout the process, so it's a very dynamic system. These digesters are plug and play. They're constantly monitored. They constantly need to know what's going in so they can control what they're getting out of it. So it's really a science, but there's also an art to it. So it's really a perfect biological commercialization project for us, where we have to combine some art and some science to get these things to work. But when they're working smoothly, it's very, very efficient. And many people do ask, what happens when material breaks down and how much biogas can I get out of it? And that answer is depends. Depends on the feedstock. Waste greases produce a lot more than a dairy manure, for instance, on a per ton basis. There's also a couple different types of digesters. A lot of the ones that you hear about and learn about are liquid-based systems, which would be these sub 15% solids, very liquidy systems. But what we're talking about with this BRDI program, when I get into talking in more definition of what we're doing, is we're incorporating what's called a solid-state digester, which looks at that 20 to 40% solids range in conjunction with the liquid digester to take in more solid-based waste streams. And then, of course, operating temperatures affect the biological system. If you think of a cow's stomach and what's going on in that, in the dairy industry, we try to keep those cows fed very consistently day in and day out. When we don't, then we have issues of all sorts of digestive issues that could happen. So that's really what we're doing here with an anaerobic digestion system. This is a picture of the facility where the BRDI field work is being done. This is a Quasar facility located in Zanesville, Ohio, so that's east of Columbus, about 40 miles east. What you're looking at there is they have a liquid digester system. You can go back if you want, but that's fine just to leave it like that, Ron. Then where the LAD, he's circling, that's the liquid system. And then the solid state system, which was built here, is a system that's kind of like a big garage, of concrete garage with a couple garage doors that we load the solid materials into. And then off to the right is a big effluent storage tank. So that's kind of the co-product coming out of the digester that then's going on and being applied to fields as a soil amendment right now. Also, right outside the solid state digester is this pre-processing pad where they're doing a lot of research in compost and things. So this is a quasar facility on Zanesville. It sits on an old strip mine. So just behind that, to the north of, or not north, but to the south, but north of the picture, behind that pond lies a big old concrete Portland cement factory that you could film a real scary movie in real nicely. But it's a huge facility that whole area is mined for coal and limestone and all sorts of things. So that whole area is a reclaimed strip mine, which is perfect for what we're trying to do, and I'll explain as we talk a little more here. This is a kind of an up-close picture of that solid-state anaerobic digester system that we're working with on a kind of a more commercial scale. It's a big system. We do this type of work in the lab, but this is one where we can look at real-world implications. So the project goal, and we'll talk a little bit more about what the BRDI program itself, this bioenergy and biofuels production of lignocellulosic biomass via AD. It's trying to integrate that liquid AD system with the solid state anaerobic digestion system for renewable energy production. That is, you can push forward there, cost effective, environmental friendly, and handles both liquid and solid feedstocks. And that's kind of key. We've been handling our liquid stocks pretty well with these systems, but we're finding more and more solid feedstocks available, and we think AD has a place. Collaborators on this particular project are pretty vast. I mean, of course, the Ohio State University, and at OSU, we have Dr. Yibo Lee, who's the main PI, and who's really the crux of the project. But in addition, we have Dr. Ratan Lau, who does our soil quality work, and Jose works for him, and Jose will speak here in a little bit about that work. Dr. Scott Shear, who's in engineering and the chair of the department I work at. He's really focusing on feedstock logistics, and we have Denny Hall from OBIC, who's a co-PI looking at the work that we're doing, which is establishing plots on this strip line ground and also looking at the social impacts of this project relative to the communities. Dr. ZT from Animal Science, and Dr. Bhavik Bakshi, who's working in chemical engineering. In addition, we have some work at Georgia looking at feedstocks modeling, and at Mississippi State, taking a biogas and turning it into a liquid hydrocarbon fuel. We have a couple corporate partners, Quasar Energy, which is our AD company, Alaterra, which is a miscanthus company up in Northeast Ohio with over 4,000 acres of miscanthus planted now, and in full production of Marathon, AEP, Case IH. So these are kind of our partners moving. It's a nice list. So the BRDI is a multidisciplined and institutional grant. OBIC, it's particular, and that's, I'm hired through OBIC, is responsible for the establishment and the continual production of corn and miscanthus plots on the strip mine soil. So that's really kind of where OBIC fits in. We're aiding and facilitating activities that need to be done relative to the field work, relative to all the moving parts to a project this large. You can move forward. That graph that was on the lower left was pretty. Look it out here in a little bit to kind of sum it up. What we have is the SSAD, which would be the solid state anaerobic digester with liquid anaerobic digestion. Our goal is to grow, take an energy crop to feed the solid state anaerobic digestion system, but to grow it on a reclaimed strip mine soil where you have depleted soils. Jose will tell you they're not even soils. They're just foreign to him, and he's had a good experience with that. We're trying to establish these perennial crops on this ground, feed the anaerobic digestion system, use the effluent to keep continually improving that production of that ground for that miscanthus, and with that perennial crop, hopefully have up to 20-year production from that crop to feed that solid state anaerobic digester. And then from that, get our co-products, our biogases. That is a way for us, one of the big issues we have with all of our anaerobic digestion systems, similar to a lot of our CAFOs, concentrated animal feeding operations, throughout the state, is that we have a concentration of nutrients within a radius. So feedstock logistics and how we handle those waste streams becomes important. The interesting and unique thing with this grant is that we're taking that effluent and using it right there on the reclaimed strip mine to keep improving the quality of the soil in an area that is nutrient depleted. You can move on. This takes that and kind of broadens it out a little bit more. How the solid state anaerobic digester works is that we actually pump liquid digestate into those vats. So as we load it with the solid material, then we take the liquid digestate and pump it into it to help inoculate the solid state system and to continue to produce the gases and to get our digest. So what we end up getting is two nutrient streams. From the liquid system, we have the effluent, which is more of a liquid system. From the solid system, we get more of a digestate, which we can do potentially compost or have more of a solid handling situation for application. We're looking at both the miscanthus plots, but also comparing that with corn production, because that's pretty much the most common denominator of production that we can kind of understand. It's a great comparison. When we started this project, those were the only two things we were going to consider. When we got to the site where we're working, we realized that the existing sod cover that was part of the reclamation project was pretty good and pretty impressive. So we actually added that as part of the project, and Jose will talk a little more about that. So we actually have 3 crops we're looking at: an established reclaimed grass situation, and then these other new use, and he's going to talk about land use changes and how that affects soil quality. Okay. So, some of the project objectives, we're looking at feedstocks, development, and logistics. So that's where we're looking at the miscanthus. We're looking at a lot of corn stover. That's where Dr. Shearer is focusing on the feedstock handling of that, and we're baling lots of corn stalks to feed into this digester. Our goal is to put miscanthus through the digester as well. So the feedstocks development itself is part of this grant, and that's kind of the miscanthus and the corn stover. Over the couple of years, we've been looking at other potential crops that haven't really moved into BRDI, the project yet, but we think there's some interesting ones that could also aid into this concept that we're talking. So that feedstocks development, this is our plot that we have established with all our different treatments. Next. With that development, we're looking at the effluent. This is us spreading effluent on the field. That's a real fun job to do when it's about 95 degrees out. Next. And then in the front, and the picture's probably small for your computer screen, but in the back was our corn that we tried to grow last year on strip mine ground, and in the foreground, in front of the person, is the miscanthus that came up and started and established well. The issue we have with this site, as we do this year in Ohio again, is lots and lots and lots of rain. So we definitely contended with late planting, wet soil conditions, and all the funds of agriculture in the last 2 years in Ohio when it comes to rain. Next. Scott Shearer, when we talk about feedstocks development, is looking at ways of harvesting corn stover, and a lot of that work's been done across the country at a lot of great institutions, and he's continuing to leverage those efforts with his own efforts to this particular project. And he's looking at some other things like how to densify these bales a little bit more for transportation issues and things like that. The other is project objective is to look at soil quality. How do we take a reclaimed strip mine and can we make it better? Can we bring it back to productivity? And that's kind of part of the strategy, and that's that full circle approach of what this project's really trying to tackle. This is where Jose will spend some time talking, and I'm not really going to steal any thunder from him. Just some basics of what you're trying to do when you look at soil quality. You look at water holding capacity, soil nutrients, carbon emissions, and agronomic traits. But I'll let Jose focus on this. The other objective is to look at biomass pretreatments for the optimization of the biogas production, and this is where Dr. Lee, is really focused and has a lot of grad students working in this area. Where how do we take all these different biomasses, and he has all sorts of solid state digester potential feedstocks that he's looking at, and he's looking at pretreatment strategies that will improve that digestion process. And he's been very successful with some of the work he's doing, and as we find those little gems, and we're trying to implement them at that big level of the AD system. And this is just some images of our lab. Up here at OARDC, for you that are not familiar, we have a really nice facility dedicated to this work that Dr. Lee manages with all his grad students. We coexist in that facility with Quasar and their researchers doing very similar work, looking at ways to improve their systems. It's a very state-of-the-art facility. I think Dr. Lee has 8 or 9 grad students at a time running through this facility. Just doing wonderful work. The other interesting part of this project that's not being conducted at Ohio State is being down at Mississippi State, is taking that biogas and turning it into a liquid hydrocarbon fuel. What we're providing them with the biogas from this project down to Mississippi State, but they have some technology and some lab scale stuff that they're looking at how to take a biogas and make a liquid transportation fuel, which if could be done economically has lots of value. You're looking at their basic concept at the lab value of how the process of what they're doing to get to that liquid fuel hydrocarbon, but I think there's some potential here, and that adds another element to what we're doing. It's a Fischer-Tropsch reaction. So I'm kind of excited about this component as well, and engaging another university. Dr. Bakshi back here at OSU is doing the life cycle analysis of this, and just stepping back and taking a full approach to how is this, what's the ramifications to these ideas. The idea, the concept that we presented and it was funded with was this full circle concept of taking a marginal soil and turning it into something special using the effluent and using AD as the technology to help us get there. He's going to make an attempt with his advanced life cycle analysis capabilities and say, yes, these things have potential, or these don't, or in the big scheme of things. So he'll take a very critical look at what's being done and how we're doing these things, and making real decisions based on hard facts and research. So the data we create at all different levels of this project, where we're harvesting, planting, doing the reactions, energy needs, he's taking all of that into consideration and really taking us just outside of our individual disciplines and bringing them all together and saying, yes, this makes sense, or these things are going to have struggles in these areas. I can't let Jose take all the thunder of the work we've done. So this is us last year. Jose got to ride in the back of the transplanter, and I got to drive the tractor. But this is us planting miscanthus last year in the plots, and we used just a tree transplanter to do it for our first year. Our corporate partner, Alaterra, was gracious enough to provide rhizomes for this work, and they have planted, like I said earlier, over 4,000 acres. It may be 45 or more now, 100 acres of miscanthus up in the northeast Ohio, northwest Pennsylvania area. And they've had those plantings established for 3 years or more. And they have more automated systems to plant on a larger scale. But the challenge with this particular crop is we're planting a rhizome and not a seed. So it requires, you think of a Sharpie, but then a Sharpie like twisted around your finger a couple times and then maybe back. It's not a real consistent rhizome. It's a rhizome. So we have to plant those. There's some other work being done at other companies looking to change the need for rhizomes, but we're planting a sterile product where a sterile plant where you need to use the rhizomes to propagate. So that's one of the challenges of a perennial crop like this, but some automation has definitely made some headway there, enough to where we can have a 4,500 acre plantation here in Ohio with it. This is last September. The miscanthus had come up. You can row it, and the picture on the right, you can see the rows that we were able to get established. Again, it was very wet when we were before we could, and the field's all spring, so we planted later than we had intended. We're kind of facing a little of that this year. So we had some concerns with overwintering. Jose will talk more about that. But we definitely had some overwintering issues, but also had some stand establishment success too. So he'll have pictures that are more recent, I'm sure. This is a picture I took at Alaterra last year when you had the peak of the growth. This is our goal. This is what we want our fields to look like eventually, and this is the three-year production fields, and hopefully they last for 10 to 15, even up to 20 years of this establishment, and with a goal of a dry biomass yield production of anywhere between hopefully more than 5, definitely up to 10 tons per acre. And Alaterra did some harvesting this year, and I think they were definitely in that range. So you're looking at quite a bit of dry matter biomass coming off the field to feed our digester for our particular project. Now, Alaterra isn't so much interested in AD. They're using miscanthus in different ways. We had hoped to have them discuss that, but they're not quite ready to share. But they're doing some really cool things with miscanthus. So the idea of establishing a perennial crop and finding uses for that, at OBIC we like to hear that because we're about bioproducts. So feeding AD is great, doing energy for fuel and burning great, but maybe other uses would be exciting as well. So what? So why does any of this matter? So really this project is focusing on improving efficiency and the cost of anaerobic digestion. Maybe potentially making an energy-dense transportation fuel. And the economic, environmental, and social impacts to a community. We think you can put something like this in a southeastern Ohio economically depraved area that has a lot of this mined ground, and look at ways to putting in these kind of systems to bring those soils back to life, to bring economic activity to those communities, and to do some really good things for some of these communities. Other so what's, a use for organic waste. I just read we've all read the article probably in the past few months that last year, 50% of all our food is wasted. So where does that stuff go? A lot of it goes to some of these digestion systems, and you'd be amazed at the things that Quasar puts through their anaerobic digesters today that are food waste. And some of the food waste you think of maybe the food you didn't eat, the table scraps and things like that, but there are tons and tons of food that just or don't make it to market that just end up having to be disposed of, and a lot go to the landfill. Quasar has been intercepting that stream a lot and making biogas out of it. So when we think of the use of organic waste in a facility, and this map shows you a dot of where the facility is at Zanesville, just east of Columbus, and if you click next once, Ron, we're looking at, that's the radius that we're bringing, the thought processes that you would bring organic waste into a facility. So I think that's about a 40 to 50 mile radius around a facility of where you could bring in these waste streams. Think of distribution centers or any sorts of things, wastewater treatment facilities. Their sludge goes into a lot of these. All sorts of waste could be brought in economically at about that radius. On the flip side, hit it one more time, Ron. When we look at where one more time. When we look at the effluent, hit forward one more time, Ron. Okay, now one more time. When we look at the energy and the soil amendments that we're producing, we're generally most economically today consuming it within more like a 20 mile radius. So what you end up doing is you're starting to concentrate nutrients a little bit to that area. So it's important that wherever you locate a facility, an AD system, that it's an area that could potentially use the effluent and use the energy and use the soil amendment that you're producing. So that's kind of the idea of why planting a perennial energy crop that you could feed the effluent to within the vicinity of the AD system makes a lot of sense. And these strip mine soils are really an area that this potentially could happen on a scale. If we produce a more dense transportation fuel, then obviously you can use it outside of that window, of that radius. But that's really what we're looking at when we look at an AD system. So when we talk about miscanthus, we talk about a new non-food energy crop that we can plant in places that are marginal soil, so we don't have that food versus fuel debate. So we have a lot of that issue when we talk about maybe corn stover and things in the areas where we produce food, but we're talking about an area right now where food production is less of a focus, and we have areas where grounds are marginal. We could use an energy crop like a miscanthus, the one we're using here, but there are others that we're exploring that could improve those soils and kind of take that food versus fuel debate, neutralize that. And now with Terra specifically focused on Northeast Ohio and Northwest Pennsylvania for that very reason as well. Again, the collaborators, just to refresh your memory, who are part of this exciting grant, if you have any questions, you feel free to contact any one of us. We'd love to tell you more about what we're doing at BRDI. You can go ahead and click next. And thank you. I don't know if we're going to take questions now or after Jose, but
we're going to take them at the end, Mike.
Okay, sounds good.
All right. Thank you, Mike. I'd like to introduce our next speaker, Dr. Jose Guzman. Jose is a postdoctoral researcher in the School of Environment and Natural Resources. Jose has a PhD in soil postdoc in the Carbon Management and Sequestration Center here at Ohio State University. Jose has a bachelor's degree in agronomy from Kansas State University, and he has his master's and PhD in agronomy from Iowa State University. Much of Jose's research has implication on how farmers can improve on more sustainable land management practices that mimic nature to improve soil quality. With that, Jose?
Okay. Thanks, Ron. Good afternoon, everyone. My goal for this presentation is just to give you an overview of what I've been doing for the past 1.5 years here at Ohio State. I'm just part of the small team at the Carbon Management and Sequestration Center who have the task to assess the impacts of the anaerobic digest application on effluent on the biofuel crops grown in mine soils. The leader of the soil quality component for this project is in co-PI is Dr. Ratan Lau, Distinguished Professor at Ohio State University and Director of the Carbon Management and Sequestration Center. And also involved in the study is Dr. David Osuri, a research scientist at the center. And the production of biofuels from renewable sources such as plant biomass is considered a sustainable alternative to fossil fuels, which may also reduce the nation's reliance on imported oils. Under the Energy Independence and Security Act of 2007, the U.S. required gasoline and diesel refineries to use at least 36 billion gallons of ethanol or biofuels by the year 2022. In 2012, they're currently producing about 52 billion gallons of ethanol, though the majority came from cornstarch ethanol, roughly about 13 billion gallons. And that corn ethanol from grain is mainly termed as first-generation biofuel. However, a cap at 15 billion gallons per year by the year 2015 was placed on cornstarch-derived ethanol. Consequently, the U.S. biofuel industry will have to rapidly produce substantial amounts of alternative biofuels, likely derived from ligand cellulosic ethanol, of which corn stover, wood chips, perennial grasses are potential feedstocks. Currently, available biomass from cropland is about 143 million dry tons per year. In the next coming 5-10 years, it's estimated to increase, or demand for biomass is estimated to increase to 500 to 800 million tons. The majority of the biomass is expected to come from corn stover and perennials such as miscanthus and switchgrass. However, concerns of bioenergy crops competing for finite land and water resources can be resolved by using only high-quality lands, soils that are highly fertile, and have no environmental restrictions, only be used for food and feed production, and thus growing bioenergy crops which have low inputs and drought tolerance, such as Miscanthus switchgrass, on marginal lands, such as mine soil. So this picture here is a picture of me about 6 feet tall, and behind me is Miscanthus, and this is from the Alaterra farms in northeast Ohio. And from the tour they gave us, they told us once the Miscanthus dries and the harvest in April, they can collect about 4 to 10 tons of dry tons of biomass. In the studies that we looked at, when they grow Miscanthus in fertile land, Miscanthus can grow up to or produce enough or about 22 megagrams of biomass per hectare, or that's roughly about 10 tons per acre. And in switchgrass, it's about 4.5 tons per acre. But again, to avoid this whole food versus bioenergy issue, growing this perennial grass and Miscanthus switchgrass on marginal land, in this case, studies done in West Virginia and reclaimed mine soils, the production from Miscanthus switchgrass was about half, and this is after 35 years of establishment. Okay. So for me, I'm doing a lot of my research from Iowa, and we have a lot of famous black soils, and we produce corn and soybean. Mine soils, as Mike said, were pretty foreign to me, and I had a lot of assumptions of mine soils. My own pre-assumptions, some of that I have were that these mine soils would have low organic matter, and this would result in infertile soils, so low in nutrients such as nitrogen, phosphorus, potassium. Low water holding capacity. I imagine these pictures of mine soils in my head of just having a lot of coarse fragments, having no soil structure, and these poorly structured soils being very susceptible to compaction. So these soils that have very little clay in them and they have no soil structure, putting any farming equipment out in the field, I would think was going to produce a lot of compaction. I also thought of mine soils being very acidic soils. And then also a lot of its mine soils, because a lot of the topsoil was removed, I figured they would have very low rooting depth, and also, I have some of the assumptions I have mine soils was that these mine soils would have high concentrations of heavy metals. To my surprise, turns out you can grow crops in mine soils. So the picture here was taken of corn growing last summer. And a little bit of background on how much of mine soils there is in the U.S. and the potential for reclaimed mine soils in the U.S. There's approximately about 1.8 million hectares of land that has been disturbed by mine soil. So this is just removing about the 10 feet or less of strip of the land of mine. So I'm not thinking about the miles deep pits like you see usually like in the Wyoming and Nevada area, not those large pits, but just the surface strip mine land. There's about 37,000 hectares in Ohio alone, and most of the coal mining in the U.S. is done in the Appalachian Mountain region. It's highlighted here in red. And so a lot of these mining sites, mine soils, are being reclaimed back to its original vegetation, mainly due to the Surface Mining Control and Reclamation Act of 1977, which required mining companies, after mining was complete, to regrade the soil back to its original topo sequence, and also to replace the original topsoil and reestablish it with the original vegetation, which in Ohio mainly meant trees. But in a lot of the cases, they relaxed the law so you can plant a grass instead of the trees, the native trees. These two pictures are pictures taken in about February, and then this one here in July, to give you an idea of what how some of these reclaimed mine sites look like. So this is quite different from the bare, large rocks, picture I had of mine soils in my head. So there is a lot of mine soil, especially in the Appalachian region, but only about 2% of it, or 45,000 hectares of the coal mine land, has been actually reclaimed. But approximately 800 hectares are being reclaimed, though. And if there's a potential, or there's a huge demand for producing biomass for bioenergy, we're thinking, we believe that there will be a push a lot of these marginal lands, including mine soils, and some marginal lands that are, for instance, in northeast Ohio, where they're growing miscanthus and Alaterra. It's too wet to plant corn. It's not profitable there, and a lot of the time they just plant pasture grasses there. If there's a demand for biomass, mainly miscanthus, a lot of these marginal lands can be converted to bioenergy production in miscanthus. To kind of remove some of the pre-assumptions of what I had on mine soils, I did a literature review of some of the soil physical properties, chemical properties in mine soils. So looking at coarse fragments, we learned that in mine soils, reclaimed mine soils, mainly in the Appalachian region, coarse fragments greater than 2 millimeters, a percentage range from 4 to 70%. On average, it was around 26%, which we probably won't see any adverse effects for bioenergy production, miscanthus and switchgrass primarily. But there, like I said, it can go up to 70%. And when you see coarse fragments above 40%, that's when you start seeing these limitations of mainly from water holding capacity. If you have these coarse fragments and you don't have the silt and clay texture to retain some of the water in the soil, that's when you start seeing a lot of the water drought condition effects on bioenergy production. And that's the 40%, the high 4% fragment soils, mine soils, usually come on sites that the original topsoil wasn't put back on. Clay percentage ranged from 13 to 50%, so that usually wasn't limiting. You need about a little, or at least 15% to be adequate for production. Compaction on mine soil is a huge issue. We saw that bulk densities varied from 1.3 to 1.7. On average, is about 1.5, which is right on the borderline of you're starting to see some adverse effects on crop production. So dealing with compaction is an issue with mine soils. But we're thinking with miscanthus, the literature says it has very robust rooting system, and we're hoping that miscanthus would help kind of improve the soil structure of the soils, so the compaction will be lower, and it should be more resistant, the miscanthus. And then again, this available water capacity. A good soil would have available water content around 20%, 13 to 20%. On average, mine soils were 13%. Again, ran in the low amount. So that's one big issue. When we look at the soil quality and in the mine soils, that's something we have to look at. How much water can the soils retain? Those are soil physical properties. For chemical properties, again, I mentioned one of my preassumptions of mine soils, whether they're all acidic soils. That's true in soils that don't come from calcareous soils. Mainly, what happens was you remove the 3 feet of soil from the surface, and you expose non-weathered rocks below that contain this iron sulfides that are then oxidized and weathered, and they release this sulfuric acid, and that's where you see this huge drop of soil pH. In our soil, we actually have quite a bit of calcium carbonate, so we didn't have that issue. On calcareous soils, average pH for mine soils around 7, and again, soils with non-calcareous parent material, those pH is a huge issue in those soils, and liming is definitely a must. So organic carbon varied by the age of the mine soil. Very young reclaimed mine soils, less than 4 years old, had about 0.7% of carbon in the soil. But then once after greater than 15 years, then you can see soils going above 2%. And here I see it can range from 7 to 4.4%. And here's 20.6 grams per kilogram of organic carbon. That's still considered very low, especially for crop production. Before this mine soils have been, all the extraction for all the coal has been done, and the literature has been reported about 50% of the original carbon has been lost. So a lot of these mine soils have a huge potential for carbon sequestration. Nitrogen has similar effects. The young reclaimed mine soils have a relatively low nitrogen, but as the years pass, nitrogens seem to build up. Phosphorus typically in mine soils are low, so fertilization, in addition to nitrogen, phosphorus, potassium, we also need to look at. And as for heavy metals toxicity, again, it depends on the soil conditions. If mine soils have low pH, we saw a lot of heavy metal toxicities. And in other mine soils, the main reason some soils had high metal toxicities is because the soil amendments that were being added to it had high concentrations of nickel, lead in them. So one of the ideas of this project was improving soil quality in mine soils, and one way to do that is to add biosolids to it. I mentioned a lot of the soils had very low carbon in them, so the soils will be inherently low and in soil fertility, and also being low on carbon indicates a poor soil structure and vulnerable soil compaction. So one way to prove that is to add biosolids to it. So when you add biosolids to the soil, you're not only adding nutrients such as nitrogen, phosphorus, potassium, you're also adding carbon to the soil to improve with the soil structure. One interesting thing about this project is the idea of closing the ecological carbon loop, and that's using the biomass that's produced in this mine soil and adding that to the anaerobic digester to produce methane and CO2 gas. But then to use the non-decomposed or the anaerobic digester effluent left over afterwards and applying it back to the field, which here we have a kind of a before and after the application of the liquid effluent. But for this study, when you're adding the miscanthus or corn stover into the anaerobic digester, we're hoping to increase the biosolids percentage of it. So to give you an idea of why that would be important, this kind of is a conceptual diagram of a soil aggregate and how it's formed. And I got this diagram from Jasper Miller in 1998. Here you see this microaggregate being held together by, in this slide, it looks kind of peachy, kind of creamy color, is the organic binding agents that hold the soil aggregates together. And the clay particles here, there's this gray, and that's being held by this peachy organic binding agents and the roots and microhyphae. So just adding carbon in soil, it's not going to improve soil structure in the soil. In fact, for instance, adding the liquid effluent that Mike mentioned earlier, having less than 7% biosolids, a lot of that carbon, it really is just, the way I think of it, just sugar. You're adding sugar straight to the microbes in the soil, and they're just going to take that carbon and just mineralize it, and most of that carbon is going to be lost to CO2 really quick, and it's not going to improve the soil structure. So you need the organic matter into the soil for the microbes to break it down, and the breakdown of the organic matter is what produces the organic binding agents, these polysaccharides that's released from microbial decomposition, and also from root exudase that glues the soil particles together. So just adding carbon to soil is not going to improve soil structures, the active decomposition of the carbon. And having the extra biomass added to anaerobic digester from increasing biosolids from 7% to 20 to 40%, we hypothesize that it will improve soil quality. And I wouldn't be a good researcher at the Carbon Management Sequestration Center if I didn't give you my definition of soil carbon sequestration. It's the way I defined it is the soil carbon sequestration is the capture and secure storage of atmospheric carbon dioxide that would otherwise be emitted to or remain in the atmosphere. So here I have a diagram of a plant in a poor attempt to draw on a corn or something. Converting CO2 via photosynthesis into carbon substrates, either carbon substrates for plant or structures. And then once the plant begins to senesce and die and leaves above ground litter and also below ground litter, the microbes then start to decompose that organic matter. And what we determine, in order to determine carbon sequestration, we consider the carbon that's stored on the soil at a decade's time to be considered the secure storage of carbon. That's our definition of soil carbon sequestration. So just adding carbon to the soil and being released as CO2, like I said, in hours or even weeks, we don't consider that part of soil carbon sequestration. It has to be a long-term storage. Kind of went over that part. So the main project that we're in charge at the Carbon Management Sequestration Center is to look at or to evaluate the impact of anaerobic digesters' impacts on corn and miscanthus production for biofuel energy in mine soil. And specifically for biofuel, the first year we didn't do it since we're just establishing the miscanthus, and it takes about 2-3 years before you can harvest. Eventually, we'll start removing the biomass from the field, so we can take that biomass and take to the anaerobic digester. So we'll also be, and during the time, we'll also be taking agronomic traits like biomass produced, plant high, some of those agronomic traits. We're also looking at the soil restorative effects of miscanthus production with anaerobic digestion in mine soil over time. And we also want to take a look at greenhouse gas balances on the different crop and management systems in mine soil. So one of the ideas also that this project is trying to pitch is that this whole system of producing biofuels from miscanthus and adding that to anaerobic digesters was supposed to lower our greenhouse and carbon dioxide emissions footprint as well, and that should be much greater than the current fossil fuel usage. So here's our experiment layout we established last year. And our treatments, we had 3 main treatments. Again, as Mike mentioned earlier, we have 3 vegetations. The C3 grass that was already there and established, and the miscanthus and corn. And we wanted to look at different sources of nitrogen, specifically fertilizer. Again, we had the liquid effluent, but we wanted to compare it with pretty much what's currently being done. So we decided to add inorganic fertilizer to compare it with, and we are planning at 3 different rates, 0, medium, and high. And we wanted to have the different rates of fertilization because in the literature, we're hoping that the miscanthus is considered to be a low input crop, and a lot of literature says miscanthus doesn't even need nitrogen fertilization. It doesn't really respond to it. So but this is on fertile land, meaning the studies were done in Illinois, where the soil is very rich there. So in mine soils, we wanted to see if that still holds true, and and especially for removing the residue from the field every year, we wanted to know, trying to figure out what the appropriate fertilization rates are for bioenergy crop production in mine soil. This is the plot layout. In our plots, this is kind of a little bit too much, but I'll give you real quick the big ideas. Our plots, we have a total of 72 plots. Each plot's about 30 by 30 feet, and the reason we wanted to have relatively large plots was we wanted to have equipment actually driving through the plots. Harvest equipment, herbicide, tillage, everything. So we have an idea what the inputs, not just and then I think inputs, I'm thinking like fuel usage for the tractors, and then also the nitrogen fertilizer, the herbicide, all those type of inputs also emit a lot of carbon dioxide emissions in their production. So that's later on, I'll get a little bit into it when we do our livestock analysis. These are all things we're keeping track of all the carbon inputs and carbon losses to see if this management systems, the miscanthus, the grass and corn, under different fertilization practices, whether this management practices are a sink or source for greenhouse gas emissions. And we have this is an experiment. We have 4 replications. So hopefully we have publications and referral journals. So we have 4 blocks. So in each block we have all the treatments here. The green plots here are the miscanthus, the blue is grass, and the orange there is corn. So a little bit of background on the site. Our site's located about 10 miles southwest of Zanesfield, Ohio. And as Mike said, it was previously mined for coal and also limestone. And it was reclaimed about 11 years ago, and most of the grass seed that they planted was tall fescue, bluegrass, and perennial ryegrass. Here's a picture of a soil profile of the mine soil that we're working with. As you can see, the top grayish area is the urban birding soil that was on top of the coal seam that the mining company extracted, and then they piled back on. They just piled it back on. It's very compacted. As you can tell from the picture here, there's a big chunk of coal there. It has about 20 to 40% coarse fragments, very little organic matter, very compacted. And then the top layer here, the dark brown, is the topsoil that was originally there and they replaced back. So last year we started. We established the plots about April, May, and the first thing we had to do was kill the current vegetation that was growing there. So we did that by herbicide applications. Then afterwards, we had to till several times to create a suitable seedbed for corn and miscanthus production. And as you can imagine, on mine soils that don't have very good soil structure, and with the wet season we had last year, and especially in the spots, the lowland spots in our site that had high clay and very compacted, but were very wet. So this mine soil took a very long time to dry, and we ended up not even planting until like mid-July. And that was mainly due just because the mine soil just being so compacted, so wet. So this is something we imagine other farmers who are thinking about using some of the nearby reclaimed mine land, that during the first year of establishment, especially, it's going to take a month and a half or so to kill the grass, till it, and eventually apply the effluent until planting. So that's some of the struggles we had the first year. So I mentioned the types of fertilizers we're applying. We want to compare the organic fertilizer, the liquid effluent from the anaerobic digester. And last year we applied it at a rate about 7 micrograms per hectare, and that was using, the 170 is about the typical N rate for corn production. And at that rate, we're also adding about 124 kilograms of phosphorus and 70 kilograms of potassium. And as for heavy metal concentrations and effluent, we applied as we're all below the EPA ceiling concentration limits. And the percent of the biosolids on effluent was around 7%. So some of the soil physical parameters that we're looking at is soil texture, filled clay, sand, as well as coarse fragments, bulk density, and soil penetration resistance to get an idea what the soil compaction in the soil land is. Aggregate stability, distribution to get an idea of the soil structure, and water retention, water infiltration. The picture there is a picture of a master's student taking water infiltration, and if you see there, this is a miscanthus. It's very bare ground. The first you see some erosion, soil erosion going on there, and we actually didn't cause that erosion from the water infiltration test. That was already there. So but that's some of the things we're looking at in our site is how much soil is lost. Some of the soil chemical properties we're measuring: pH, electroconductivity, can exchange capacity, nitroammonium, phosphorus, other micronutrients, and as well as concentration of heavy metals. Some of the biological properties: microbial mass carbon, again carbon and nitrogen, and also greenhouse gas emissions, mainly carbon dioxide, methane, and nitrous oxide. And here's pictures I thought were representative of the first year so far of the study. Here we have corn, and you can see we were just surprised it even grew on mine soil, so we thought it was a huge accomplishment. But you can definitely see this is just one plot that you can see a little bit of yellowing, that you see a little bit of nitrogen deficiency, and also the middle rows are stunted compared to the outside rows. And this is, you can't really see the tire tracks, but that's where the heavy tanker went over. the mine soil, and that's where we start seeing a lot of the stunted growth. So again, soil compaction in mine soil is something we definitely have to look into closely. Here we have miscanthus last year. Again, we were happy, thrilled that it grew, and we had a very good establishment actually. But it only grew up since we planted so late in July. It only grew about 3 feet tall and only having about 2-3 tillers. Right now, about a week ago, the last time I was at the field, the miscanthus is about 4 to 5 feet tall now, and it has 6 to 8 tillers now. So it looks like it's growing, and we're hoping by third year we'll have something that kind of looks like the miscanthus that was growing in the Ashtabula pictures that Mike was showing. And the grass that's already established there, you can tell how drastic the difference between the first year miscanthus compared to the grass. So the establishment year miscanthus during the first year is something definitely we have to look into on the land use effect. So in the long run, you can see miscanthus producing a lot of biomass and the ground being covered. But what's the carbon depth? What's the loss of soil erosion during the first year of the establishment? That's something we need to take into account for. I also mentioned that we wanted to do a life cycle analysis on carbon and greenhouse gas emissions. So we're measuring all the carbon inputs and carbon losses from herbicide applications, planting, mineral fertilizers, even harvesting, the cutting and baling. We're taking into account all the carbon inputs from the management inputs, and also measuring the carbon outputs, as well as carbon dioxide emissions again. And we're also measuring some of the carbon inputs as biomass and effluent that we're adding to soil. We're keeping track that with the carbon losses to see whether this management is either a net gain or net loss of carbon and greenhouse gas emissions. Some of the main results of this project that will provide answers to the following key questions. We want to look at the effects of anaerobic digestion on miscanthus and corn biomass yield. We also want to know how much fertilizer is needed to offset yield losses due to nutrient removal from biomass harvest. Effects of anaerobic digestion on miscanthus and on soil restoration and on previously reclaimed mine soil. How much carbon sequestration in the soil with management practices, and are these management practices a singular source for greenhouse gas emissions? So some of the references I cited, and
all right. Someone may have put us on hold. We're getting some music, so please ignore the background music.
Background music. I think we've had a couple of questions. We've gone a little bit over today, but if we'd like to go ahead and try to address those for some of our listeners that are out there. Max, if you want to start real quick, we'll try to answer them as fast as we can.
All right. I think the first one was answered. How do you measure how effective the effluent is at improving soil quality? I think that was an earlier question. I think you've already answered that one, I believe, in your presentation. What are the relative amounts of CO2 and methane in biogas? Is the ratio always the same? I'm not sure if that's a question for you, Jose, or maybe for Mike.
Well, the ratio is not always the same. It's a relative situation based on feedstocks. You can never really predict exactly what it is, but the ratios that we presented were roughly the normal range.
About 2 to 1, is that right, Mike, typically?
Typically, yeah.
So 2 parts methane, 1 part CO2. Okay. Next question, with the current boom in natural gas production via horizontal drilling, have you seen any decrease in interest for natural gas via anaerobic digestion?
That'd be a great question for Quasar. I think their perspective is no. It opens up an infrastructure for more use of it. So it gives them an alternative product to say that we're more sustainable. So I think they're actually excited by the explosion of CNG and natural gas because it opens up new markets.
Yeah, we're hearing from Quasar that they are expanding and they're getting a lot more contracts. I think because that infrastructure is there to allow them to do more with it. So I've also heard the same thing from Quasar Mike, so that's very important.
Absolutely.
Do you need special, for example, more durable equipment to harvest crops on mine soil?
Not particularly, probably not. I mean, obviously you're going to want to make sure, the concern of compaction is a big issue, like Jose pointed out. So we may look at things like track machines or things like that try to reduce compaction problems. But as far as trafficking, see that being a huge issue. I'm sure we definitely have to beef up a few things here or there, but it's nothing that we can't really accomplish.
All right. Well, I'd like to thank our speakers today, Jordan Stacy, Mike Sword, and Dr. Jose Guzman for presenting. We also want to thank all of you who've hung in here and joined us this afternoon as participants. We'll hope you will join us again for our next event on July 25th at 1 p.m., which will be a webinar on the innovations and applications of PLA to various new markets. Membership in the OBN network will ensure your access to great programming opportunities such as networking events, annual meetings, will help you keep your company at the forefront of happenings in the bioproducts industry. So we'd like you to visit our website and then take a look at our application. Again, we want to thank you for participating, and we look forward to having you again with us soon. Thank you.